In this section, we'll look at Rotary Positional Embeddings, or RoPE, a widely used way to give language models a sense of token position. We'll start with the core idea, how RoPE encodes relative position through rotations in attention, and then connect that to why it matters in practice for long context performance, model implementation, and interview-ready intuition for LLM engineering roles. Here's the agenda for this section. We'll start with the core problem: why large language models need positional information at all. Then we'll look at what RoPE does in plain language and where it sits inside the attention mechanism. After that, we'll cover practical tooling, including RoPE scaling in real model configs. Finally, we'll wrap up with interview questions, strong answers, and a few portfolio-ready project ideas. Here's the core problem. Transformers don't understand word order on their own. Self-attention sees tokens more like a set. So, without positional information, the dog bit the man looks no different from the man bit the dog. Absolute positional encoding adds a fixed position signal, but it struggles beyond training lengths. Learned embeddings have the same limitation. RoPE solves this more elegantly by encoding position through rotation, giving models a flexible relative sense of order. Here's the core idea of RoPE in one sentence. It builds position directly into self-attention by rotating the query and key vectors based on each token's position. That means the attention scores naturally capture relative distance between tokens. What changes is that Q and K are rotated before the dot product, while V stays the same. Everything else is familiar: standard attention, no position lookup table, and no extra learned parameters. Here's the intuition behind the mechanism. Position acts like a phase shift. As a token moves, its query and key vectors rotate in embedding space. We split Q and K into two-dimensional pairs, rotate each pair by an angle based on position, and then compute attention with the usual dot product. Tokens at similar positions stay better aligned. Distant ones align less. In an interview, this implementation pattern matters more than deriving the full algebra. This slide shows where RoPE fits in the attention stack. We start with input tokens, turn them into token embeddings, and then apply the linear projections that produce queries, keys, and values. RoPE is inserted right after those projections, but only on the queries and keys. Then the attention dot product is computed. So RoPE adds positional information exactly at the point where attention scores are formed. The RoFormer paper made RoPE influential for three big reasons. First, it's flexible with sequence length, so the model isn't tied to one fixed context window from training. Second, it gives a natural decaying dependency, where attention weakens as tokens get farther apart, which matches how relevance usually works in language. And third, it's compatible with linear attention methods, so it can work efficiently beyond standard quadratic attention. Here's a quick comparison of RoPE with older positional encoding methods. Sinusoidal and learned embeddings are added directly to the input, while RoPE is applied to queries and keys, which lets it represent relative position more explicitly. RoPE also handles longer sequence lengths more flexibly, without adding extra parameters. That combination of efficiency and better positional behavior is why it's become the standard choice in many modern large language models. RoPE has clearly become the default positional encoding in modern open language models. It's built directly into major open-weight families, not treated as an optional research feature. The LLaMA series, including LLaMA 2 and 3, uses RoPE with configurable scaling. Mistral and Mixtral also rely on RoPE, including sliding window attention variance. And across models like Qwen, Gemma, and Phi, we see the same pattern: broad, ecosystem-wide adoption. In real model configs, RoPE shows up under RoPE scaling. In Hugging Face's LLaMA setup, this is where the theory becomes something you can actually tune in production. The factor sets how much farther the context window can stretch, relative to the original limit. The type chooses the scaling method, like dynamic, long rope, or LLaMA 3. An original max position mClagans gives the baseline context length that all of those scaling calculations build from. Here's the basic idea behind context extension with rope scaling. A model might be trained on a 4K context window, and then we scale its positional embeddings, for example by 4, to let it accept a nominal 16K context. But that doesn't automatically mean it performs well across all 16K tokens. The longer window is theoretical until you test it, so real quality at extended lengths always needs empirical validation on your specific tasks. When we talk about long context trade-offs, rope scaling can help extend a model's accepted sequence length without full retraining. That makes longer retrieval, document question answering, and multi-turn memory more practical, and it can often be configured at deployment through the model settings. But it's not a guarantee. It doesn't ensure token quality at those new lengths. Stable attention far beyond training, or strong task performance, unless you validate it with benchmarks. Here's why product teams care about rope. In RAG systems, longer context means you can include more retrieved chunks in one pass, which improves answer quality. For agent workflows, context limits cap how much history a multi-step agent can carry. Coding assistants need room to see larger portions of a codebase. And for long document chat, especially in legal research or enterprise settings, rope configuration is often the first lever to extend usable context. Beyond the theory, these are the career skills employers actually look for. First, documentation literacy. Can you read the RoFormer paper and a Hugging Face model card? Then connect the ideas to real settings and configs. Second, implementation literacy. Do you know where rope appears in the forward pass and how it affects attention kernels like flash attention? Third, evaluation. Can you verify whether longer context really helps? And finally, communication. Can you explain all of that clearly to both PMs and researchers? Now, let's focus on interview prep by looking at some of the most predictable interview questions and how to answer them well. The goal isn't to memorize a script, but to prepare clear, confident responses that highlight your experience, strengths, and fit for the role. When you know what to expect and practice strong answers ahead of time, you'll come across as more polished, professional, and authentic in the interview. Here are the 4 rope interview questions you're most likely to get. First, what problem does it solve? It adds positional information to attention using rotation, which preserves relative position and supports flexible sequence lengths. Second, how is it implemented? By rotating the query and key vectors before the attention.product, not the values. Practically, people care because most modern LLMs use it, and context extension often relies on rope scaling. Finally, evaluate task quality, not just token limit. Here are 3 portfolio projects that show real understanding. First, benchmark rope scaling settings on long context tasks like document QA, codebase summarization, or multi-turn memory. Second, trace where rotary embeddings appear in an actual forward pass, and measure latency and memory with optimized kernels, such as flash attention. Third, build an interpretability notebook that visualizes how attention shifts as sequence length grows under different scaling choices. Rope is a great topic for career growth because it sits in the sweet spot between depth and breadth. You can learn the core ideas from the RoFormer paper, then connect them to real production tools like Hugging Face and flash attention. From there, you can build and benchmark your own implementation, document what you find, and practice explaining the trade-offs clearly to both engineers and non-technical audiences. The winning signal is the difference between surface familiarity and real engineering readiness. Surface-level knowledge sounds like rope is a positional encoding, or being able to name the paper, or having used open models without ever touching the config. Engineering-ready people go further. They can explain the Q and K rotation before the dot product. They know the rope scaling settings and types, and they've actually benchmarked context quality in practice. Here's the bottom line on RoPE. It encodes position by rotating the query and key vectors, which gives you relative position effects without adding new parameters. That's why it shows up everywhere in modern open-weight models like LLaMA, Mistral, and Qwen. In practice, extending context is often a rope scaling configuration change, not a full retrain, but you still need to validate quality, and that paper-to-product understanding is exactly what teams value.